How often do you look at the ingredients list of normal household things, or even your food? Or do you ever see those posts going around talking about how dangerous things that you can't pronounce are just because you can't pronounce them? Have you ever seen Breaking Bad and wish you understood half of the chemicals they were talking about? Or do you want a Jimmy Neutron moment of being overly verbose to prove how smart you are? Well, look no further. Join me today as we talk about how they name chemicals on this episode of Why Are You Talking About This? Hello, everyone, and welcome back to another episode of Why Are You Talking About This? I am your host, William, and today I'll be your chemistry teacher. Future me? Hat. Cool. But before we get into the episode, make sure to like, comment, and subscribe. Also, this week, make sure to go check out past episodes. I have a pretty significant backlog, and I've been re-listening to them. And holy shit, I've always had some bangers. Not to toot my own horn, but I'm absolutely tooting that shit. Also, make sure to check out my friends. Go to Winkashka's stream and watch them play hella cool games, do some chatting and singing, and hey, maybe one day, if my entire schedule isn't a nightmare, I'll be able to join them on one. Also, go check out Mystic Luna at Shopify and also at weekend markets, where they're doing art shows across the beautiful state of Oregon, basically every weekend from now until forever, basically. They make really cool jewelry and art and deserve the support. And of course, speaking of art, make sure to check out Captain Cupcakes at the link in the description. They are my amazing, awesome, beautiful girlfriend, and I have no idea what I'd do without her. But that's enough shout-outs and calls to action. I think we can get into the show now. Alright, so before we really get into things, I think it's valuable to talk about the point first, since, I'm addicted to making episodes that have a point instead of just making them for some reason. When I sat down to make this episode, I initially did it with the intentions of teaching you how to identify a chemical, if it's, safe or not, and what it even is. But when I started to actually do research on this, I realized I can't really give you a helpful guide with that. Because that's not how naming conventions work, and also not how chemistry works. But the thing that I did realize is that while it's not universally applicable, learning how chemicals are named is still useful information. Because firstly, it makes science a lot less confusing. If you can understand the logic, you can understand vaguely what most things are made of if you know its chemical name. Secondly, a ton of people will try to use these longer, complicated names to trick you. For example, someone trying to make a food sound scary to make you buy their mystery pills in the back alley of a Whole Foods might well say something like, "Hey kid, did you know that stuff contains a dihydrogen monoxide 2-hydropropane 1,2,3 tribocarboxylic acid mixture?" Now, sure, that sounds a bit intimidating, but that's the two primary ingredients in lemon juice: water and citric acid. So hopefully, if you understand how naming conventions work, it'll be less scary and something that you can break down yourself, learn about by looking up the name, or maybe, hell, you even know what its common name is. And of course, third, this is incredibly valuable for world builders, especially if they're building in sci-fi. Also, elephant in the room, sometimes it's just good to learn shit. I mean, did me talking about superpowers for multiple episodes serve much of a purpose besides telling you how some parts of the human body works? No, because you're never going to use that. But what you will use is the information on how eyes work and how hearing works and how things interact with your human body. This time I'm just taking off the training wheels for you. You got this. I believe in you. Now, getting into it, when a compound gets named, the first step is determining if it's organic or inorganic. Now, an organic compound is always going to have hydrocarbons in it, or carbon-hydrogen bonds, and look really fucking complicated. Let me tell you, they are complicated. But the difference is really, one is stuff that makes up living things, or can be created from things that are or used to be alive, and the other one isn't. Yeah, inorganics tend to be a bit simpler. But once the thing you're looking for is determined to be inorganic, basically not being composed of long links of hydrogen-carbon bonds, then you need to look at the kind of compound that it is. These would be monoatomic ionic, polyatomic ionic, covalent, hydrogen covalent, or oxygen covalent. Now, our two ionic compounds are held together in a similar way. They're held together through the attraction between positive and negative ions, like how the strongest relationships some of your friends have ever been in are hot fucking garbage, even though they are a ray of sunshine. And an ion is basically anything with a positive or negative electron charge. They only form from a metal giving their electron to a non-metal, creating a crystal lattice structure. Basically because that's the only way they go together. In this case, the metal would be the positively charged cation, and the non-metal is the negative anion. Now, a monoatomic ionic compound would be a compound where all the cations and anions are the same throughout the whole thing. Think like a heterocouple. Easy to understand, but not unwelcome if they aren't toxic. Now, the way you name these are taking the metal's name and then following up with the non-metal's name, with the back half replaced with the suffix "-ide". Like, take sodium, a notably explosive metal, and bond it with chlorine, a notably poison gas, and combine it together like pen, pineapple, pen, and you get exactly what you are in COD lobbies. Salty. More specifically, table salt. And yes, that's the only time I'm going to use that meme. It's old and dead. Now for a few more examples. Aluminum and nitrogen forms aluminum nitride, and potassium and bromine forms potassium bromide. And of these three chemicals examples, which of them can you crunch and munch on? Salt, at least until your doctor begs you to stop. And okay, I mean, you could crunch on potassium bromide, but it's not recommended because it's a dog seizure medication. So unless you and Fido are going to trip shit on sedatives together and then go to the hospital, don't do that. Now, really don't eat aluminum nitride. It turns into ammonia gas when exposed to moisture, so unless you want to know what it's like to huff World War I-ass chemical weapons, just don't do that. But anyways, polyatomics is when we get slightly more difficult. These are ones that are ionic bonds that are bonded to either a covalent cation or anion. Basically, they're experimenting a bit and added a third in. Now, this means you need to name the polyatomic ion, but once you do that, then you just do the same process as the monoatomic metal first. But you don't change either name. So if there's no metal, then you go with the positive one and then the negative. So, for example, magnesium phosphate, magnesium sulfate, or calcium carbonate. Or calcium carbonate. Calcium carbonate is found in shells, chalk, and marble, and is used to make antacids, paper, and paint. Magnesium phosphate is a mineral supplement and is added to food as an anti-caking, leavening, emulsification, stabilization, and acidity regulation agent. In processed food, it's also used to fortify stuff like dairy and baked goods. Don't eat it raw, however. The level that they put in food is not toxic, but if you just start shoveling handfuls of it, it's pretty toxic. And potassium sulfate is plant fertilizer. Don't eat that one. Also, don't just go around eating chalk or handfuls of magnesium phosphate. That's really fucking weird. Now, while I used harmless examples, not all of these are. Something like sodium hydroxide is a lie. Aluminum nitrate is bad to breathe in, is also an explosive agent. Just so you don't get confused that, like, these are always okay. Anything in chemistry mixed together could cause issues. But okay, let's get to how to name those polyatomic parts of the ionic bonds. Covalent bonds are bonds where the atoms involved share electrons. They're very strong and stable and have a solid outer shell. They also tend to be non-metals. When you combine them together, you need to count out how many different elements are involved, since they tend to get a little freaky-deaky. And if it's just two, then it's pretty easy. The compound name is an order of least to most atoms with a numerical prefix on both elements and "ide" on the second element. So mono, di, tri, tetra, penta, hexa, hepta, octa, nona, and deca. So if you were to write CO2, you'd write carbon dioxide. You could technically write monocarbon dioxide, but it's not really necessary, since if something comes first in the order and nothing else says to the contrary, it makes sense for that to be the one. Now, when you add ite or ate out in the when you see ite or ate out in the wild, that's generally the amount of oxygen atoms. If it's equivalent to the oxidation number of the other atoms involved, which is basically like, hypothetically, its charge if it were to all be ionized, which doesn't necessarily happen out in the wild, but it's useful. Then the name ends in ate. Otherwise, it ends in ite. So like nitrate is NO3, while nitrite is NO2. And what do you do if there's more than two chemicals? Shit and cry. And then clean yourself up and follow these steps. Firstly, treat it like it's ionic. Starting with the compound furthest to the left of the periodic table, write out the covalent bonds, following the same rules as the polyatomic ionic bonds. So if it's something like NO2S2, which I don't think is an actual chemical, but good for demonstration, then you'd write out nitrogen dioxide disulfide, which is a mouthful, but you're probably not going to encounter that one very often. And often, when you do, it'll be part of an acid, which is what we'll be covering next. If it's a binary acid, then it'll have two traits. First of all, it dissolves in water. Secondly, when dissolved in water, they become acidic. To denote this, it's named by changing hydrogen into a prefix, hydro, and giving the other word the "ic" suffix, followed by the word acid. So like hydrogen sulfide, a highly toxic gas, when dissolved in water, turns into hydrosulfuric acid. Or hydrogen fluoride, another dangerous gas, becomes hydrofluoric acid, etc., etc. Funnily enough, most of these guys are going to be horrifically toxic before they're an acid. So if you're near something labeled as hydrogen something-ide, best to stay clear of that and really don't try to put water on it for some reason. Now, oxyacids are complex structures, something we tend to see more in organic chemistry. Trust me, you'll see in a bit. But an oxyacid is a compound that has a hydrogen, oxygen, and at least one other type of atom. Usually these are polyatomic structures that hydrogen forces its way into. To name these, you'll just take the "ate" ending and replace it with "ic," or the "ite" ending and replace it with "us." Since it contains oxygen, it'll have that ending anyways. Then add acid onto the end of it. So take a nice mixture of phosphate, PO4, and add on 3 hydrogen atoms. Well, now we have phosphoric acid, or a nice CO3 or carbonate to create carbonic acid. Easy, right? Yeah, these guys you should probably avoid too. Phosphate is a preservative and supplement, but phosphoric acid corrodes metal and causes severe chemical burns. Carbonate is used in both glass and soap, and is also, found as part of part of calcium carbonate. Carbonic acid, however, can cause some pretty severe environmental damage, although you'll probably be fine if you eat, like, small amounts of it. Don't do that, though. If you encounter random chemicals out in the environment that are concentrations like that, don't consume them. Now, you might also encounter hydrates. These have water in their chemical structure, like borax, gypsum, or Epsom salt. While in the modern day we tend to just add water to the end of the compound's name, we still do sometimes use the old system to name these things, where you add a number prefix to the word hydrate, at the end of it. So like gypsum's chemical name being calcium sulfate dihydrate, since it has 2 water molecules in it, but under the new system it would also be calcium sulfate of water. Speaking of older systems, it's also pretty common to still encounter those, even though it's not used in science anymore. So we'll go over those. Bi used to be a common prefix, meaning a single hydrogen atom inside of it, which we see in sodium bicarbonate. Also, different levels of oxidation states used to have different names. When applied to cations and acids from lowest to highest, it would be hypo at the beginning, hypos at the end, hypo at the beginning, us at the end, ick, per at the beginning, ick at the end, and hyper at the beginning and ick at the end. While for anions, it would be hypo at the beginning, ite at the end, ate, per at the beginning, ate at the end, and hyper at the beginning, ate at the end. And this stuck around, being used in things like ferric chloride, sulfuric acid, things like that. But with that, let's get into organic chemistry, which is the whole science of hydrogen and carbon bonds, and is what makes up me, you, your mom, your dog, and several billion other things across the planet. Beginning with alkanes. These are ringless single bonds following the general formula of CnH2n+2, which basically means for every single carbon, there's 2 times that plus 2 hydrogen atoms. And these form the basic alkane structure, continuous and branching chains of these compounds. And for most of these, you use the numerical prefix from above, like the inorganics, and then add the ending ane. I mean, sometimes there's a jackass that adds an N to the beginning, but we're not worried about that today. Now, the first 4 of these hydrocarbons, as they're called, are actually only referred to by their common names. These are methane, ethane, propane, and butane. These 4 serve as our foundations for naming everything else. Now, this is if they are straight. If they're twisty, bendy, branching, alkanes have a slightly different name. Firstly, you use the longest continuous chain to act as the parent name, using their name directly. Like if a straight, simple line of hydrocarbons, 4 in a row, then that's a butane. Then add onto it the substituent groups. You name these guys the same, but with a YL suffix, and assign a number prefix corresponding to where they land along the chain. And the more onto the chain, you add a prefix to denote how many there are. For example, let's say there's 3 branches. Each of these has only 1 hydrocarbon, and each hydrocarbon would then be named methyl. That gets added on for methylbutane. But since there's 3 branches, it's trimethylbutane. And to show their positions relative to the main chain, you say 2,2,3-trimethylbutane, because they're attached to the second carbon twice and the third carbon once. Sound good and complex to you? Also, when there's multiple substituents, always go in order alphabetically. Also, if you see the term iso and neo, don't worry about it. They're 1, falling out of favor, and 2, fairly simple. Iso means there's 2 methyl groups at the end of a straight chain, and neo is used to say that there's 3. Now, cyclocanes are similar, but are in a ring. And this is one that you see a lot. These guys kind of form the foundation of a lot of organic chemistry. And as you might imagine, for something so fundamental, its name is pretty easy. Just apply cyclo to the beginning of what its straight name would be, like how my straight name is Gregory. Now, the substituents are assigned numbers and put in order that would make for the smallest numbers. So if we imagine a ring of 6 and one substituent is at the top and the other is at the bottom, then you have 1 to the bottom left, then they'd be 1 at the top, 2 at the bottom left side, and 3 at the bottommost point. And the substituent groups themselves also get names. They're named by replacing the ane at the end of its name with YL if you had to remove a hydrogen to bond it. Otherwise, you add alkali cyclo or cycloalkali, depending on how freaky you like it. Although you usually see the first one used a lot in science. Now, see, not nearly as scary as you thought, right? So let's try this out with our example compound above. So using the process of twisting it around, its name would be 1,2,3 trimethyl cyclobutane, which is actually a chemical. It doesn't have a common name. I don't know what it's used for, but I looked it up. It is a chemical. Also seems like that there's not a whole lot of information on what exactly it does. My guess is it's like a foundational chemical that's used in other organics. Okay, but now it gets weirder. These are alkenes. I'll be saying it like key to differentiate between this and alkanes. Now, the reason for their name being so similar is actually for a pretty good reason. Because they are very similar, but they have a double carbon bond. Basically, the carbons share an electron. And this makes the formula come out as CnH2n. So it's basically, for every one carbon, there's 2 hydrogens. These are usually called olefinic, since they usually turn into oils. But more broad is an unsaturated hydrocarbon. Now, you name these mostly like an alkane, but your base name is the longest continuous double bond chain, and you replace the ane with an ene. And then you number it with the double bond being furthest to the left and the lowest number possible. Alkylenes are similar, but you add ene to the end of the alkyl part. So instead of ethylalkali, it's ethylene. And if you derive the thing from an alkene, the name's end is changed to ENYL, enyl. And cycloalkenes are again similar. Always start the numbering with one of the carbon double bonds and continue through it to keep the numbers low. If the hydrocarbon group is double bonded to a single cycloalkane ring carbon, the suffix aldene, ylidene, or ylidene, is added. And the alkadene is anything with 2 or more double bonds, which is actually a double suffix. Because if it has 3, it's an alkatriene. If it's 4, it's an alkatriene, and so on. You basically cut the alka off and add the rest on as a suffix. And the bond type tells you a bit too, like the accumulated double bond and the standard. If it alternates double and single, it's conjugated. And if it's neither, it's considered an isolated. Then are our triple carbon bonds. They form the formula CnH2n minus 2. And these guys end with YNE rather than ANE. And the naming system is named the same way as the alkenes are. Those with more than a triple bond are called alkadienes, alkatrienes, etc., according to the number of triple bond hydrocarbons. These are called alkenynes. Okay. I should have apologized earlier. I'm going to apologize now. I have a hard time mouth differentiating a lot of vowels, which is also kind of why I have a hard time pronouncing a lot of things in general. I'm trying to break them down. I've also looked up pronunciations, It's just not happening with my mouth today. I apologize. Um, but these are numbered to have the lowest possible numbers. And finally are aromases, also called aromatic hydrocarbons. They are the ring-shaped ones of this type. However, the ways they function is very different. We won't really get into that, but the way you name them depends on the hydrocarbon substituent names. Benzenoids, or ones with benzene in them, are called the phenyl group. Also, depending on their relationship to the benzene, they can be called orthos, metas, or para-isomers. And they're named very similar to the alkylenes. But that is as far as I got into organic chemistry. Everything beyond this made my brain melt, and even this, I needed to have several breaks a day. So, in order to not melt your brain or continue to melt mine, let's talk. Let's take it to the end. All right, hopefully that was informative, if nothing else, and interesting otherwise. And hey, if nothing else, science all that big and scary anymore? Sorry if the answer is yes. Anyways, thank you so much for watching and listening. If you have opinions, improvements, corrections, anything else you want to talk about, comment below or email me at waytatpods@gmail.com. And remember to like, share, and subscribe for more. Also follow my podcast feed for audio versions, and come back next time when we feed some adventurers. Have a good night, don't murder, have fun, and remember, don't drink chemicals. Except the ones you're supposed to, like water. This has been Why Are You Talking About This, and I've been your host, William. Good night.